Okay, so the pros and cons of different, I guess, approaches to calibration. This is just a bullseye diagram kind of illustrating differences between precision and accuracy. So this is the danger zone. When you use sensors right out of the box, you buy them, you get them, you use them right away, no checking the data. So the danger zone is that they're all wrong and they also don't agree with each other. And if you try to do your monitoring project, if you don't do any calibration, you really can't draw conclusions from the data you get. And then this is like a less worst case. Maybe you choose a golden sensor. If you don't have access to a reference monitor, you choose a golden sensor and then you adjust all the other sensors, you calibrate it to the golden sensor. So even though they may all be wrong on a quantitative level, at least they're all close to each other, like they're all responding the same now after calibrating to the golden sensor, that you can draw qualitative conclusions. You can identify a hotspot. So if two sensors are now doing this, at least the difference in their response is meaningful. Whereas if you didn't do the calibration, if you're in the danger zone, that you can't draw any conclusion from their different responses. Another possibility is maybe you are able to do a field collocation to do a calibration, right? But then from that field collocation, you only derive one calibration function, and then you apply that one calibration function to all the sensors. So all the sensors, they'll all be closer to the truth, but they're all going to have their own little individual difference from that one calibration function you apply to them. So they're all going to be close to the truth, but they're still going to have some good spread that it'll be hard to kind of draw conclusions about why, whether if one sensor is showing something different than another, you can't really conclusively say. And then finally, of course, the ideal situation is if you could calibrate all the sensors against a reference monitor and then apply an individual calibration function specialized to each sensor. Okay, so the training part when you're deploying sensors or when you're getting ready to deploy a sensor. So if you have a small team or a single person doing the sensor deployment, it might be good to just have a written up standard operating procedure. This would ensure more consistent installation. Good for smaller projects. If you're having a single person or a small team deploy sensors, this could get very expensive for large projects. The other way you can do this, if you have a very large project with a lot of sensors, is you can have the sensor hosts. You can train the sensor hosts. So let's say you're doing a community air monitoring project, right? And you have, 20 of these sensors, and you give a sensor out to each household. You can try to write up some very clear, simple instructions to pass out to the participants and hope that they can follow these instructions close enough so you can get more reliable data than opposed to if you didn't really provide much training. There might be a hybrid approach. You could train the trainer, so perhaps there might be some really engaged members of the community or really more technically expertised people in the community. You could train them, and then they can go ahead and do more individual trainings with each of the households, and that might be another approach to making sure that everybody is doing this on a consistent, in a consistent way. These are just some examples of don't do this, do that. So don't block the airflow wherever the inlet of the sensor is. Don't put the inlet inside a bush. Try to make sure there's clear, open airflow around the inlet. If you're trying to do some measurements to kind of characterize more ambient air quality or regional air quality, you don't want to put the sensor close to a source like a cooker or something that's going to show these high spikes. But if you're trying to understand what the regional air quality is, because then you're going to get, your data is going to be improperly influenced by these sources that are not really relevant to your project objectives. And that's the same thing. Just make sure there's open airflow around it. Sunlight can affect the temperature of the sensor. Temperature of the sensor can affect the response of the sensor. So if possible, avoid placing it in direct sunlight. There is a northern southern hemisphere thing. You're so close to the equator, it may not matter whether you put it on a north or south facing wall. If you get a lot of rain, you want to also have a drip loop. So if there's a power cord, make sure there's a low point. So if there's any water collecting on the wires, it can drip off and not into not into the electrical points. Mounting height. So if you're doing a personal exposure study, as Steve mentioned very well, make sure it's, or I think was covered during the Q&A session, make sure it's like somewhere around here on the person in the breathing zone. If you're doing ambient or source monitoring, we recommend at least 2 meters high. And there's a lot of other great advantages to mounting sensors as high as you can, because that avoids sampling like resuspended dust from the ground, assuming that that's not part of your goal of measuring resuspended dust. If you have to be on solar panels, you'll get more sunlight exposure. If the sensors transmit data through cell signal, they'll have stronger cell signal. And also, if you can mount them higher, it's harder to access for theft or vandalism. But on the flip side, that means it's also harder for you to access when you have to do maintenance on them. I don't know how much of an issue it is here, but in Los Angeles, when we have sensor networks there that we operate and maintain, and one issue that we run into a lot is theft. People steal copper wires from the street lamps. It's terrible. In fact, in Los Angeles, we built a new bridge. It's very beautiful. And then, I think 2 weeks after the bridge was opened, all the street lights didn't work anymore because all the copper wires were stolen. So we have copper wires being stolen. So if the sensor was plugged into the street lamp, that now means the sensor doesn't have power. Some people will just want to take the sensor. So we've seen sensors taken down on the ground and just kind of dented and smashed. They didn't even want to take it. They just wanted to destroy it. Sad. Okay, sensor maintenance. So usually the sensor user manual should have enough material for you to know how much, what kind of activity to do for maintenance. It would be great to create a maintenance schedule so that the members on the project, this should be part of the standard operating procedure, the SOP. Everyone's on the same page of how often and when you're doing, activities to clean the sensor, wipe the dust, blow some compressed air inside the PM sensor to get the dust out, maybe changing replaceable or consumable parts of it. So common actions are just cleaning. There might be accumulated dust or spiders or other insects inside. If you just blow some compressed air, you can kind of clear that out. You might need to replace a battery or a solar panel because those things eventually they start not working as well over time. And especially for the gas sensors, the electrochemical cell or the metal oxide sensors, again, those things, they typically have a lifetime of 1, maybe 2 years if you're lucky, and then their response kind of, it's not really usable. So you have to make sure you're on top of replacing those on a regular schedule. And then you might want to consider midway through your project, right? Reevaluating the locations. Because maybe when you did all your planning at the beginning, you thought, okay, I want to measure this and this and that, and so I got to put the sensors here, here, and here, and here. But maybe midway through the project, you realize that certain locations that you thought were good are not so good because now there's a bus that parks at that spot every day, and you didn't know that, and it's just influencing the readings all the time, and it's messing up your project. So reevaluating and relocating sensors to better locations partway through your project. And then also, you want to, if possible, do recalibrations because the sensor responses, they'll drift a bit throughout your project. So if you can periodically readjust them back to some truth, that will keep the data quality of your project high. And there's a lot of different approaches you can do for recalibration. This is a great little table that I stole, well, I cited them though. It's from the EPA sensor guidebook, kind of showing different ideas of how you can co-locate sensors and keep them calibrated through a project. So you could take all the sensors, bring them back to the reference monitor and do another co-location and then redeploy them. Or you can do a certain subset, maybe like these two come back, get co-located and then redeployed, and then these two come back and do it. So you can stagger them so you don't ever have a period of time when you have no data for the project, right? You can also have a reference transfer, or remember that golden sensor? If you have a golden sensor, maybe the golden sensor can travel around to the different spots and you can adjust all the deployed sensors against the golden sensor that gets to move around. And that's the same thing as that last column, sensor transfer. There's also this thing called remote techniques. This could be a very attractive way for you to keep a network of sensors calibrated when you don't have a lot of reference monitors available. And it does involve a lot of staff time to get somebody out to the field readjust or recalibrate your sensors or bring sensors back and forth. So there are remote techniques. I'm not the most expert on remote techniques, but there's models and statistics and distributions and some ideas of how you can transfer distributions and kind of removing background signal to try to do some adjustment of your sensor signals without actually having to go to the sensor. But that's not something that I'm as familiar with. And again, I think if you really want to get to a quantitative defensible truth or highest data quality, I think that does involve some work of getting some ground truthing of bringing sensors back, getting them co-located and recalibrated. Other good practices to make sure your data quality stays high is if you have the ability to remotely monitor some sensor health metrics. So for example, if you can remotely see the sensor values, there might be some instances where you'll see the values get stuck at 0 for like days. And if you can remotely keep track of that, then you know that you need to send someone out to the field to go take care of that sensor, right? Or if you see that the data completeness, if every hour a certain sensor is only sending a few readings, that's a data completeness issue. And if you're able to remotely see that problem, you can send someone out to the field to go handle that one as soon as they're aware of it. Or battery issues, or sending someone out. If a sensor system has duplicate sensors, one good example is the Purple Air, they have 2 plant towers. If they have duplicate sensors, you can look at the correlation and the errors between the 2 channels, and you might have some kind of metric that if it exceeds that metric, then you go send someone out to the field to go check up on it and maybe replace or do some repair work. Okay. Shoot, I have 5 minutes. Okay. Data quality control. So these are some QC tips. I think I kind of already covered this. But yeah, if possible, if you have a way to kind of, if you can look at the data periodically and do some QC checks regarding sensor values or data completeness, or even looking at other aspects that are not related to the data but to the sensor, like the battery charge, that could give you some indication of which portions of data you should not use in your analysis because it's questionable, and which portions of data are good that you can keep for your analysis. And you can do these data QC checks in a lot of different ways. So there are simple and real-time QC checks that you can do, like as records are coming in real time. There are very simple binary checks you can do to flag a record as being valid or invalid. So obviously if a value is non-numeric, blanks, negatives, out of the range that the manufacturer said it should be measuring, or if there are any error warnings, messages that came with that record, that's a pretty simple QC check to implement because it's just a binary yes or no, did it do this or did it violate that. There are more complex or post hoc checks that you can do after you've collected the data and you bring it back to the office and you look at it on the computer. You might want to check, remember how I said earlier, if you keep good documentations and records during the project, that makes it easier to go back to find, if you have a problem with the data, you can go back and see what happened. So you can check your data against documented periods of maintenance, calibration. Maybe there was a no incident where that supports your removing that data from your analysis. Checking for data completeness, checking for flat lines or stuck values, and also possibly doing some outlier identification. So sensors, sometimes they'll get stuck on a value for a whole bunch of different reasons. Maybe they're stuck on 0 because there's not that much of that pollutant, or maybe it's so dirty that they got stuck on the highest level. Or it could be due to a sensor component, like an electronic failure of the sensor. So there's